Alrighty, cool. Well, welcome back to the stream. A little technical difficulties there. So now that I am streaming, I told my mom about this stream, so she gonna watch. So I'm gonna send her a link to this. If y'all will stand by while I send that her direction. She's learning all about Twitch, and she was asking me, do I go to the Google and then to enter twitch.com into the Google and do all that. But I helped her out, and hopefully she got her account set up and so on. So I hope she hops on the stream. So let me send this to her.
During this build today, are you going to construct additional pylons?
I'm going to modify the phase variance a little bit.
Yes. Full stop.
Yep.
I'll get Patrick started in full stop.
Oh, man.
He really hates it when the card says full stop because it's like,
Yeah.
relation to what?
Yeah, exactly. So, like, you're flying in space, right? Okay? And, like, you know, Jean-Luc Picard is like, hey, yo, I'm, like, driving my freaking spaceship around. Oh, let's come to a full stop here. And it's like, a full stop is only a stop with respect to other things that are stopped. Like, other things that are fixed. So, you can't actually have a full stop in space unless you define your coordinate system, right? So, if you have a full stop, the only way that would make sense is if you consider, like, if they have mapped the entire observable universe and it is not changing, it's not expanding or doing anything like that, which just, that doesn't make a lot of sense. Or it's like, you've defined a sector, right? And then you've said, okay, this sector, we are picking certain points and calling those things fixed, and we are, like, relating our own locations to those things, and that just, oh my gosh, yeah, it doesn't make sense.
Yeah.
Doesn't make sense.
If we were in Starfleet and I was your captain and I asked you to come to a full stop, what would you do?
I would tell you that.
No, you can't question me.
I would be like, Captain, why are you a captain? How are you a captain? What does that mean?
Well, you wouldn't have.
How would anybody obey that order, Ted? How would anybody do it?
I'm sure they would obey it to the best of their ability.
He wouldn't say it because it wouldn't make sense. Alright, I digress. Alright, I got the link set up. Yeah, I guess this is why I'm not in Starfleet. Okay, so, from last time, we got one component placed on this little circuit board here. But this is the CY8C4013LQI-411, which is a tiny little microcontroller from Cyprus. And I bought a whole bunch of them and made little breakouts for them. And today we're going to see if we can get one populated and testing and potentially get code onto it, because that would be cool. So in the background, I'll adjust my camera over there. So we got Laz and we got Ted, and they're working on some stuff, but they'll be in the background there. So I'm currently at my place of work. You can see things are covered up because they're super duper secret. I'm hoping I don't accidentally expose any top secret things here in the background. Hopefully not, but what I'm doing is just going to be over in this area here, and you can see over on this other let's see, this other scene, I have this really nice USB microscope, and it's far better than the setup I had yesterday. And there you can see the pitiful excuse for a soldering job that I tried to do yesterday. Didn't quite accomplish it. But there you go. That's the at least one of the pads soldered down. What I'm probably going to do is start fresh with a new one, and then using actual solder paste and the proper tools and things, go ahead and get it all situated on there. But what's nice is I was talking about over here, you've got this little like silk screen, that white line there. That's the pin 1 indicator that I've made for the part, and then the actual component has this little dot here. So these numbers, this is sort of the part number and all that kind of stuff, and package information and all that. For the microcontroller itself, and they burn that in there with lasers. And what's actually kind of cool is like sometimes if they're really secretive, or they're trying to be like intentionally misleading so that people can't reverse engineer circuits or anything like that, sometimes they just won't put any indicators on there. Or you'll even have people that like sometimes they'll place components and then will mechanically like etch them off. So it's like they have in their factories people with sandpaper that will just scratch the top of these chips so that like they can't be identified. And that makes it really hard to like, you know, get the code off of them and do all that kind of stuff. So, but this particular guy, it has some security features inside of it. We're not going to be focusing on those. This is mostly about just getting a little cheap microcontroller to talk I2C. And all right, so this is a fresh board here. There's the pads, and you can see that these things they look kind of shiny because they have a finishing on them. So it's copper underneath that silver stuff, but that silver stuff is it's just solder, and they call that hassle, or hot air surface leveling. And when you have hassle, basically you just sort of like you smear solder paste across the top of it, and then just have a hot air gun that just sort of like just like blasts it, and it blows off any excess. But covering the board with that layer of solder, it helps prevent like corrosion and stuff, and it makes it easier to attach components later. So what we're going to be doing, let me toss that little piece of tape away. So I have this big old chunkin' thing. So this is the stencil that was made by who made these boards? It was JLC PCB out of China, Shenzhen, and it's way too big. So I think the first order of business is I'm gonna see if I can find some tin snips, and like, because all I care about is just those little cutouts in the middle. And it would be nice if this like stencil was smaller than the physical area of the board itself, right? So I'm gonna see if I can just sort of like cut an outline there and then tape it to the surface. So I'm gonna go grab some tin snips real quick. See if we have some in here. Which I don't even know if we do. Is the sound coming through okay, Les?
Yeah, it is.
Cool.
I mean, it's delayed, so I either have to like put the headphones on and just watch the screen,
Yeah,
or listen to it.
that's true. Yeah, I got buffering and all that sort of stuff set up for the camera and microphone and so on, but I wonder if
So I had to mute it so I could. It's weird to hear like.
yeah, it's definitely hard to follow those sort of things. I don't want to use scissors because that's gonna totally like fuck these things up. All right, Laz, would you mind running to you like out? You know where the back door is?
No, but I can find it.
Okay. Yeah. So like the back corner, like over there, there should be a guy named Zach who's working on his car. He might know where some tin snips are, or some sort of like metal snips for. Sorry. Cool. Thank you for checking on that. All right. So while Laz is going to check that, I'm gonna assemble some of the other components here, and I guess the first order of business is you can see on this guy here. So I have like C1, R2, R1, all these different passives. I never specified the actual value for them, but it can be somewhat flexible. I don't think it's super important that these things behave exactly, you know, to some sort of specification or whatever. We can be a little sloppy with it. So let's see. What I want to do is we have these awesome kits at work. So they're made by Aid Tech, I guess. I'll put this here, but these things are like, you know, it's basically this massive sampler box of like different valued resistors, and this all comes in a same package, right? So these are all like 0805, 0805 size. But we also have like 0603s and 0402s, but it makes life really, really easy when you have to populate something, because you can just sort of like pick the resistors right out of that rather than having to deal with like reels and so on. All right, cool. Last found some tin snips. So I'm gonna take this and we're just gonna trim this up. So gonna do this. Doop, doop. So see, they got a little protective coating on the back there. So you can always remove more material, but you can't add it back. Do a rough cut first. Clunk. Yeah, it doesn't put a nice clean edge on here, but for our purposes, we don't need one. It's like, you know, there we go. Got a tiny little guy here. That should be okay. It's still larger than the actual layout of the board itself, but it should get us by. It'll give us something that we can attach the board to. So we'll line this up, you know, make sure that our board kind of lines up in there, and then using solder paste, which is just sort of like, I don't know, it looks like some sort of like gray peanut butter kind of consistency, but you smear it on there, and then you use a little like squeegee tool to like force solder paste through the holes on this stencil. And when that happens, it helps control the amount of solder that you're putting on there. Go figure. And what's nice about that is it makes it really easy. So it provides a tacky surface once you have the solder down there to stick all your components to. So you don't have to worry as much about them falling off the board and stuff, and they kind of like stick in place. And then once you heat it up, the surface tension of the solder will sort of cling to the component lead, and then will also cling to the the pad itself and sort of pull it to the right spot. And there's a little bit of a subtle art to making your components in a way, your footprints in a way that like makes that happen more successfully. Because like if you something that can happen if you make your components wrong or you design your boards a little sloppily is you can have this thing called tombstoning, where if there's, say, like a tiny little lead and then a big fat, I don't know, ground plane or something that can like suck away heat really easily, you end up having like asymmetric heating of the pads, and one pad will like the solder will liquefy faster, and it will cause one of the components to sort of like stand up on its edge, just because of the surface tension alone. So you want to try to make it in such a way that it like evenly heats everything up, and you want it to all like liquefy all at once, so it can reflow. And all right, so I guess first order of business, something that's kind of cool is GLC PCB. When they ship the boards out, they actually included tape. So it's like nice, easily removed tape, so you can like do your stencils. I assume. So how is this gonna work? Yeah. So what I think I'll do first is, might be able to do it under here. That could be kind of cool. So let's go to microscope mode. And all I really care about is getting the right solder paste for that guy. Woo! Focus, yeah. There we go. Boop. Perfect. So I will take this. I will tape them down here on the corners. Actually, what I can do is, because this is only for surface mount components, I can tape over the through hole components and not be in the way of any of the solder stencil things. So just kind of putting these over broad swaths here. Just trying to secure it as best I can. Oh, geez. Okay, guess not. That was not good. Maybe this tape is not as great as I thought it was. Alright. Hopefully that'll be good enough. If I just don't jostle it. Maybe. I don't know. If it moves too much, I might just grab more tape of a different flavor. What I would like to do is see if I can get this lined up. There it is. And okay, so it's getting there. And go ahead and say that that's pretty darn good. Okay, so now I'm going to secure this. Let's first taking some, this is a big old solder roll here. I'm going to place it on top of the board, so I'm going to lose microscope shot for a little bit. Oh, actually, that's interesting. Just look right through it. It's got a spool in there. So that's going to hold this in place. I'm going to readjust because it moved a little bit. Okay. And then I'm going to find some Kapton. Or something a little more durable. Yeah. So Kapton is a it's this kind of like orange yellow tape, and it's Kapton is sort of like the brand name for it, but it is also the actual material is polyamide or polyamide. I don't know, depending how you want to say it. And it is nice because it has really good thermal performance. You know, so you can put it on really hot things and it's not going to melt until like really high temperatures, and it's also electrically inert. So a lot of times you'll find this in like electronics type you know, applications. Pretty common in this industry, this space. Ooh. Ted or Laz, would one of you guys mind posting the link to this on one of the Riot channels?
Yeah, definitely. I just did it on the Facebook.
Nice. Cool.
There's only one like on that. So.
That's okay.
What's in the panel up? Doing Jack.
I'm not on the Slack anymore.
Oh, you're not?
You should do that.
Yeah. Okay. Still just sticking this thing down.
I would have to reset my password and do that.
That's alright, I got it.
So I'm gonna put one more piece of tape down, and that should be secure as all frickin' frick. So each of the different 4 sides. Whew, yeah, secure. Okay, so this stuff here is solder paste. So it's called Chip Quick, and Chip Quick. They have a whole bunch of different products and stuff, but this is their solder paste, and as you can see, you open it up, it's got the consistency of like, I don't know, like peanut butter. Let me see if I can get a light in here. Whatever, tilt it up like this, I guess. But it's this is a mixture of what is it? 63% tin, 37% lead, with some sort of like water soluble flux in there. So you can like rinse these boards off afterwards. And, you know, because there's lead in it, you know, there's always that danger. Lead is in no way, shape, or form good for you. But it also has really, really nice metallurgical properties, and, you know, we tend to use it for doing reworks and stuff like that. And it's, yeah, you know, as long as you wash your hands afterwards, you kind of practice some reasonable safety, like, you know, don't eat anything while you're in the lab, wash your hands often, all that kind of stuff, and that will keep you safe for the, you know, for the most part. Don't eat the flux. That's basically all you got to do. Or don't eat the solder paste.
Everything in moderation.
Everything in moderation. There you go. So I think I might just make a squeegee out of this.
Did you check the solder drawer?
I didn't.
See if there's a squeegee in there.
Oh yeah. So, as you can see, this is an official solder paste spreader. All it is just it's like a credit card that doesn't have any magnetic strip on it. It's just a piece of plastic. So it's just something that you can use to scoop out the paste. You put it on the stencil and then just smear it across, kind of like a, what do you call it? Like a t-shirt silk screen operation. And I would like to, let's see. So my roommate was doing some of this for, you know, actual work last week, and using this wonderful, like, you know, to continue the weird, gross peanut butter analogy, using a kitchen butter knife to stir it up, because in much of the same way that like your peanut butter, the oils will kind of separate and like come out of the suspension, you also have to mix up your solder paste. And like it looks like a paste because it is a paste, but it's actually these like microscopic spheres of metal with like low melting point. And those things are what like melt and create a, you know, whatever proper like surface coating to stick your electronics to. But it just looks like a goop because of the flux and the tiny particles in it. But you can see, scooped out a little bit. Let's see if we can focus on that. Probably not. Oh yeah. Oh yeah. That's cool. So, I'll take this stuff. Gross. And then smear it on the top of this little board here. That's way more than I need. So, I don't know if we can see that. Yeah, it's this big old blob. Not that great, but you'll see shortly what it looks like when it's properly spread. As properly as I'm capable of spreading it anyway. All right, and then there you go. That's it. That's the process. Magic, huh? All right. So take the excess. I'm putting it back in the tub because I don't need it. Put it to the side. Doesn't contaminate our surfaces. The excess off of that knife there. And yeah. Start peeling this tape off. So that helps us, because like what's a big problem when you're dealing with these tiny components is like, you know, metering out the right amount, because it's super easy to put just tons and tons of extra paste on there, and this is a nice way to sort of like properly meter that out, in kind of an automated way. So what we can do then in the future, because I only want to make one board now just for testing, but we can build a little jig for this guy, or even just like, you know, remove the tape off of 3 sides so it has what's like a hinge, and then you lift it up, you put another board in, you tape it down in place, line it up, and then repeat. And if we're doing a ton of these things, they actually come in like big frames, much again like a t-shirt silk screen, and then just a big old squeegee, just 2 hands smearing paste all over it. You know, you can do like, you know, tens or hundreds of boards in a single swipe, but it's that's more of an industrial process than we're really looking to do here. But you can see from the microscope here, it's all perfectly ladled out, which is super nice. And what I was unable to do in my stream yesterday is this here. So you can see the opening for the solder in that center pad was smaller than the actual pad itself. And that helps the component when it sits down on there. Like, once it reflows, it wants to create this sort of like this pillow that it sits on top of. So I'll swap out the one that I just did, and this is the one that I did yesterday. When I put the, come on, you, where is it? Yeah. So when I dabbed a little bit of like solder on there, you can see this blob over on the left side. That comes from putting too much solder down, and when I like seated the component, it squirted out from underneath it, which is not the end of the world. It just means you got to do extra work to correct it. But the stencil put the perfect amount on there. So, hooray. All right, so then let me get some different resistors and capacitors here from our fun box of fun. All right, I'll probably switch to, let's see, I'll go to screen grab here. So that way you can see kind of the process I'm going through here. Oftentimes when I build a board like this, I'll have either the schematic, well, not either. I will have like the schematic and the PCB open just so I can see where parts are being laid down, what their values are, and come on, there we go. sometimes they'll have the bill of materials. And there's a really cool tool in KiCad called KiBomb, and it kind of does like a cross probing. So you'll like select something on your bill of materials, and it'll highlight it for you on the printed circuit board and also in the schematic and stuff. And it's really useful for doing just this. I just haven't configured it for this computer, but I'm hoping, man, it's hard to navigate this thing with the trackpad. Really got to get my mouse out. Okay, so we can see that this is the microcontroller here. Well, I don't know if you can see it. Let's center it. Woo. This guy here. This is the shift register for lighting the LEDs. I don't actually have this part on hand. I got some other shift registers, but what I'm probably going to do is I'll reflow it with the solder that I put on here, and then from this I'm going to attach leads coming off of it, and that'll allow me to attach one of these guys. What did I done do with it? Either one of these or one of these. They look like the same part, but they're different shift registers, just kind of pulled out of storage. Just trying to make do with what we have. But in the meantime, let's see if we can rotate the board so it's the same orientation as this guy. And then, all right, so we want to look at R1 and R2. These two guys here are pull-up resistors for the I2C lines. And when you're dealing with pull-up values, I2C has a, like, the specification calls for like a certain rise time and fall time. Because these guys, so this bus is open drain or open collector, depending on what transistor type you have, but that means that it's either left floating or some device is connecting a data or clock line to ground. And when it's left floating, you need to pull it to some high value. And what's nice about that is it sort of lets you sort of pick whatever your high voltage is, and you can set the resistors such that your rise time is somewhat tunable. So if you have a really low value resistor, that's referred to as like pulling up harder, and if you have a big value, then it's a slower rise time. So it's all just a compromise between like power consumption and performance. So depending on your values. So, but normally for I2C, it's going to be somewhere around like, I don't know, 1K to 10K, somewhere in that order. So I'm going to drop this one here is a 3.92K kilo ohms, which is not important to be that exact value, but not important to be that exact value, just somewhere-ish in that range. And I don't know, worst comes to worst, we can swap it out with something else.
What's the voltage reference?
So the voltage reference is VDD-IO, and in this case, I think VDD-IO is going to be set to 3.3 volts. And so these guys here, what's nice is the solder paste is a little bit tacky. And you kind of get that in place there, you touch it down, and now it's sort of like, it's stuck. And what I also really like about 0805 parts is that they're large enough that they can actually put indications on there of the size of the resistor. Once you start getting into like, I think 0402s and smaller, you can't actually get numbers on the resistors themselves. So you have to just sort of trust that what you're picking out of the bag or the reel or whatever it is the right value. So that there, these C values, I think I'm gonna go between like 1 and 10. Sorry, 0.1 and 1 microfarad. Which again is just sort of like to help the power rail stabilize a little bit. I don't foresee this being a crazy power hog or anything like that. Those are, I think, last time when I was designing this board, I brought up a like capacitor simulator site by Kemet, and there is a lot of engineering that can and should go into choosing bypass capacitors and all this kind of stuff. But for this like quick and dirty example, I'm gonna I'm gonna pretend that's already been done. Okay, so what I'm gonna do now is grab another one of these little one of these guys. So this is the reel of 200 microcontrollers. I'm gonna take another one and pull it out. Place it on here. So gotta make sure I find the correct like pin 1 indicator, and then you can see. Let's see if I can get the lighting a little bit better. Woo. Doing like it's auto focusing here. Got to get that light kind of going across the surface so you can see the, you know, because it's like it's a laser cut, so it's not depositing any material, it's removing material. So you have to create that contrast with the light kind of coming from a side angle to see the things. But you can see in the upper left there, that's the pin 1 indicator, and then I'm just going to place this in this orientation on that pad. As best I can. Once I kind of center it in there. So this little microscope that I'm using, it's really cool because it can do, it's got a display on it, but frick. Yeah, it's got a display on it, but the display turns off when it goes to USB audio, or sorry, USB video. So I have to look at my screen over here while I'm working on it, rather than the one that's built into the microscope. Okay, so that's pretty good, and it doesn't have to be perfect because, like I was saying, the surface tension of the solder should pull that into place. This is Ted.
I am Ted.
Hello, Ted.
You're gonna put the rest of the components on before you blast it?
I'm only gonna put a couple more components on. I think there's only 2 resistors on this whole board. I think. Let's see. So just those pull-ups, and then yeah, the rest are just capacitors. So I'm gonna sprinkle some capacitors on here, and
Sprinkle.
yeah, ice cream sprinkles. Our capacitors, unfortunately, are not organized in the same sort of way. That's okay. The same sort of way as our resistors. Because there's more variables to them. So there's the package size, but there's also the value. But at the size of the capacitor and the value, you also have a rated voltage. So you now have like a 3-dimensional parameter matrix to choose from rather than just 2. And it makes having big boxes of them on hand just a little less convenient. One UF 16 volt 085. Yeah! Cool. So this is kind of our do-it-yourself solution that we've come up with. I'm holding it really tight because these latches aren't that great on here, if there even are latches. But you can see here, maybe, this one here, it says 1 microfarad, 16 volts, X7R 0805. So that's the capacitance rating, the voltage rating, the dielectric, which is sort of it's the temperature coefficient of it, and then the package size. So that temperature coefficient says that like across different temperature ranges, your capacitance is going to change within a sort of like specified profile. And X7R is really nice. It's pretty stable. The most stable, like you use capacitors when you're building like oscillators. So the oscillator crystal uses the capacitors to sort of like drive itself into like self-resonance, and you want that oscillation because you want a consistent clock, because that's why you have a clock in the first place. You want your capacitors to maintain their capacitance rating across their whole like expected temperature use case, so that when you have these crystals, the clock remains consistent across the entire temperature range. And that dielectric, they call it like it's C0G or NP0. I don't know. They all have like really weird cryptic names that need to be, memorized or researched or whatever. But I have a big table for. But these guys, these are pretty good. I don't need to be using X7Rs. I don't need to be using X5Rs or anything like that. I can be using garbage caps for this thing, but it's here and it works. So we're not going to be seeing, these things are rated for 16 volts. I will not be experiencing more than 5 probably. And yeah, I'm just going to go ahead and plop them down everywhere. So let's go back to our microscope view and let's put these guys here. I also don't think I have the voltage regulators, but what I'm going to do is attach some lab power supplies just as kind of a stopgap in the meantime. So that should be fine. So I just got to make sure, I think all of these are bypass caps for the 1.8 volt rail, the 3.3 volt rail, and input power less than 15 volts. Yeah, so I think it's all just bypass. So it doesn't need to be any specific value, because sometimes you have like RC, resistor times capacitor is, so resistance times capacitance is seconds. It's kind of like a unit conversion thing, but you use it for setting, like if you're doing timing specific things. So you can, like the 555 timer is like a super popular circuit that people use, and it is set almost entirely by resistor and capacitor values.
Are those happy little capacitors you're putting down?
These are happy little capacitors. That's right. And there are no mistakes, just happy accidents that sometimes make your circuits blow up.
Yes.
And if your circuit blows up, that's okay, because that means you're letting the magical electron pixies fly out into space. Every time a circuit blows up, a pixie gets its wings.
Slack Maggie asks, which microscope is this?
This microscope is it's made by a Chinese company called Hayear, Hayear. And yeah, so it doesn't have a model number on it. I was looking for that earlier. It says Hayear and then full HD 1080p 4K. So you can find it on Amazon. It's a black microscope, and I think we also got a zoom lens attachment for it. I think it was something like, I don't know, like $250 or something like that. But yeah, it's pretty nice because it does 1080p. If you use the HDMI output on the microphone, so you can set up a monitor that like basically just serves as the primary display for this thing, and you can blow it up to tremendous sizes. But if you want to do it like I'm doing here and use it as a USB webcam, unfortunately it's only 720p. dropping capacitors around here.
That's only partial HD.
It is. I want full HD, man.
I want 8K.
That's right. I want the video projected directly into my visual cortex. Now that's lossless video I can get behind. Who needs eyes? Not me.
Until we do it and then we find out you do need eyes. Like, oh yeah, the eyes I guess do some of the processing.
The eyes are windows to the stomach.
Food.
So again, just sticking these things down. Boop, boop, boop. And I think I'm gonna put, let's see, I guess 2 more capacitors on there. I can't see in my mad dash to get this board done. You can see that like here in the center, there's something between those 2 capacitors that says what it is, but I need to pull up the board here to see what I'm actually trying to do. This is near J1. J1 is a 2-pin connector with like the input power and stuff. So you can see here, this is a pad underneath here. It's just a ground port. So there's a capacitor here, here, and here. So they're all 3 in parallel. And you might know this, you might not know this, but like in parallel, capacitors add, where in series they have a, what is it, product over sum type thing, calculation. And it's the exact opposite for resistors. So resistors in parallel have product over sum, like equivalent resistance, or yeah, equivalent resistance, while you know one resistor in series with another one, they just add. So it's kind of an interesting sort of relationship there. So I think just 3 more capacitors. Oh no, there's only 2 in this thing. Okay.
Doesn't, it means off. Open it up, we're going to clean it.
Open it up, gonna clean it out. Alright, so I think these are all the components that I want to put in place for now. I'll go back to the microscope view here. So got my capacitors all stuck down. Man, you know what I want to do? I want to do this on the hot plate rather than the hot air gun.
You can bring over the hot plate over there.
That'd be cool. Okay. I wonder if I can set up. I wonder if I can
Microscope on top of the hot plate.
Yeah, that would be cool.
That would be scary.
That would be scary.
But can you have the platform facing one way and the microscope the other? Like if you turn the top of it over so you have the platform, yeah. No, so you have the microscope facing to the back, like if you had the hot plate behind it. Get what I'm saying?
Oh yeah. So this thing at the base here can probably unscrew, rotate. I don't know. That might be something to try another day, but it might be something to try now. Who knows? Woo.
Could be like a cooking show. You just put that to the side, and it's like, here's one already done. You pull one out of the oven, like, oh look.
Yeah. So right now, whoa! Don't mind me. I am unscrewing my lens. It's about to get real weird in here. Ah! Oh no, you can't see anything anymore. Put the not so zoomy zoom lens back on here, which is gross, by the way. Holy crap. That has not been taken care of. Okay, pull that off of there. and then screw it in here. We'll see if we can get that to focus. Oh, it's almost the same. That does not provide any. Ooh, get real close there, but I want to get the opposite of close. Yeah, sorry about this. I'm still figuring out how cameras work. I'm new to this, man. I want to get that camera far away and then in focus. So, okay, well, whatever. I think, you know what? I'm gonna turn down for what?
Slack Maggie asked, "Is this your home workspace?"
This is not my home workspace. This is my workspace. I was working with this stuff at home, but I didn't have all the supplies. One thing that is going to make life really, really nice is this guy here. So this is a, what is it? It's a Hako 850D, like temperature controlled heat gun. And what it allows you to do, as you can see here, it's got this nozzle on it. With this like big long tube coming off, and you can set exactly the temperature of air coming out of here, the rate of air coming out of here, and you can replace these nozzles depending on how you want that that hot air distributed on your circuit board. So what I'm gonna do is I'm gonna turn the air control pretty far down and set it to about, I don't know, 1,000 degrees. No, because you want it to like not be too crazy hot, because you don't want to like have localized heating in certain areas and stuff. This honestly, because I only have components on one side, it would probably be easier to do this on a hot plate and just heat everything from the bottom and let all the heat kind of soak through the printed circuit board. And as it like goes through the printed circuit board, then it'll sort of like melt everything all at once. But just because I have the setup already here, I'm going to be doing the hot air gun. So, you know, and it should be fine. I don't think we're going to have any major issues here. This is like, what is it, like 300C, 400C, something like that. I don't know. It's pretty hot. But what I need to do here is I'm going to kind of like go through this soak process. So as I get a little bit more air control here, I'm going to pass this tip over the top. Oh, that's cool. You can actually see the turbulent air as it like it comes out of here and distorts the camera view. So I need to kind of like get some of these like these big ground pores. A lot of those things are big heat sinks, and they can cause problems if you kind of ignore them. But if I focus a little bit here, what's nice about it is you should be able to kind of like see the reflow process as it happens in real time, and that's cool. As you can see, oh yeah, there we go. First, it like spreads out a little bit because the flux gets all liquidy, and then it dries out a little bit and looks like it gets all hard and crispy, and then it gets shiny, and all those tiny little microscopic balls all pull together at once. It's a really, yeah, there it is. It's a like oddly satisfying thing to watch. You can see that it's starting to kick. And you can see one side, that capacitor on the bottom, C4, it's, you know, reflowing for one lead first. And another way to do this, I've seen a lot of people do, is they convert like toaster ovens into reflow ovens, so that they can have sort of like a consistent temperature profile to them. But yeah, some sort of like oven that you bake these things in. So there's so many ways to deal with surface mount components, which is really nice.
Hey, Patrick,
What's up, Ted?
Slack Maggie wants to know if you can talk about where you work.
Sure. So, well, Ted and I, we both work at a company called Ologic, and what we do are kind of like consulting projects for electronics. And what that means in this particular instance is like a lot of times folks will come to us and they'll say like, hey, I've got a napkin sketch of, you know, how I want to build a certain project, and we will work with them and say like, okay, cool, well, you know, you say you want this, that might be tricky to do, let's try to like see how this could work, make it a manufacturable product, and like basically work with startups and, you know, even like mega companies to like figure out how to build like certain electronics projects, and go from like either small run prototypes, so we'll do like one-off projects where we make like, you know, 10 of something, all the way up to like, you know, huge consumer products and projects where, you know, we're making like 100,000 of them. And like, you know, what changes about your design requirements as you like deal with all of these different you know, I don't know, different scales of operation and all that kind of stuff. So it's really cool, and it's neat to sort of like see how a bunch of people try solving different problems, and like, you know, everyone's got their own unique requirements that that follow their projects, and we get to kind of say like, okay, well, based on your, you know, your pretty specific requirements there, this is how we can meet them for this particular use case. And, you know, so it's a lot of like printed circuit board design, a lot of like firmware, a lot of microcontrollers, and, you know, stuff like that. And even like I would say probably like 60% of the work that we do is in robotics. So you know, you'll see like somebody will say like, okay, we have a robot that, you know, drives around hotels, and we need this robot to operate elevators. How do you get a robot to operate an elevator? You know, how do you get a robot to, like, I don't know, ring someone's doorbell, and those sorts of things. So it's a constantly changing like landscape of different requirements to satisfy, and yeah, I don't know, just a bunch of really neat things. So that's sort of in a rambling nutshell kind of the stuff that we do.
Next question is, how old is the business?
The business, I think it started in 2005, something like that. So this is a slow boat over here. So I'm cranking up the heat, or the airflow a little bit. Because, so, I mean, like, underneath this this printed circuit board is a... Ooh, actually, that's a really good point. There's a big old chunk of metal, and that chunk of metal is very likely pulling a bunch of heat out of the printed circuit board as I'm trying to, like, melt the solder, which is very disadvantageous to what we're trying to accomplish here. So what I'm going to do is find something that isn't going to burn, but is also kind of insulating, and see if we can try to heat it up on that. So plastics, ooh, cardboard. I said hopefully won't burn. This might burn, or better yet, the stencil came on a piece of like sacrificial MDF, which is like medium density fiberboard, and take off a little chunk of it. That might be a reasonable insulating barrier. So if it starts to smoke too much, then I will probably try something else. But in the meantime, let's give this a go. smoky smell. Kind of tilt my camera over this way. So currently just heating it up and hoping this dang thing will do what I want it to do. Oh, cool. Alright, so as you can see, I like jiggled it around a little bit, and then it moved back into place. That is a good sign that it is all reflowed. Alright, and now that's the microcontroller there. I'm going to kind of go to all the other spots around here, make sure that they're properly soldered in place. And what's especially going to be tricky on this board, so like here on this capacitor collection, C15 and C16, they're going to want to basically reflow on the right side, but not as much on the left side. So I got to make sure that they get properly stuck down. And then what I can always do here is come back with a soldering iron and touch these things up with a little bit of solder if it didn't look like they really like stuck down properly. And it's a little bit of a manual process, kind of obnoxious to do, but you know, whatever. Nothing's perfect. Congealing. Dang. This is less fun than using a hot plate. Ooh, and what I also have, which might make life easier, thought I had it, is flux. Do I have flux?
Yes. Flux pen.
Yeah, not a flux pen, flux syringe. Thanks. Nice here. So, this is the same flux that is like inside the flux capacitor. No, it's inside of the solder paste, and is also like inside of the rosin core solder. But what this does is it just sort of like makes solder more sticky, and just sort of acts as a really nice way of helping things stick. So, when in doubt, use more flux. There we go. Perfect. Look at that. There it is. Reflowing like a champ. So, adding a little bit here. Go back and touch these guys up. Fluxy flux. And then what I'm going to do after this, make sure everything's stuck down. Then I'm going to probably clean this off with some isopropyl alcohol. Just to sort of like, one, to get these, like, if there's any solder that isn't totally reflowed on there and they're just sort of like still little solder balls, I would really like to remove them so they don't accidentally cause shorts. And also to just sort of get some of the flux residue off, because it's a little sticky and gross and, you know, not nice to handle, just from a pure comfort standpoint. But yeah, I think that is about, that's about it. I'm going to call that done for now. Maybe. Yeah, okay. So I'm gonna let that cool down a little bit. I'll show it off on the main camera here. So let's see. I should actually be pulling up the chat here. How old is the business? 2005. Yeah. Oh, nice. Daniel Robert Lewis is on here. Still a little toasty, but there we go. Boom. Check it out. So we got our microcontroller on there, our capacitors, our 2 resistors, and then the next step here, once we clean it off, is I want to attach leads to that that surface mount part in there. That's the shift register, and that way we can still control the LEDs. But with a different part. And then those little like through hole things, just gonna add some headers, and well, Bob's your uncle. So I think, I wonder if I should try to search for shorts. I don't know. Looks good enough. All right, I'm gonna go grab some cleaning materials. These guys, just a little container of isopropyl IPA. Just do a little scrubbing. Ooh, actually, instead of IPA, we can goof off. An even more aggressive solvent.
It won't melt in 64 plastic. It's not even melt.
Well, it's a good thing my my board isn't made out of N64 plastic.
That would be weird if it was.
Yeah. All right, so goof off this stuff. Pro Strength remover. It removes Pro Strength. So just kind of slather that on there. Just kind of get that all soaked in. Blah, 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 blah. And give it a light scrub. And what I'll do is, after this thing's been sort of scrubbed for a bit, I will wipe it down with a little Kimtech wipe. I kind of wish we had Q-tips, but I think we're all out.
Well, we have some.
You sure?
Cotton swabs?
Yeah.
Yeah, I'm using some right here.
Oh, dang. Okay.
Don't have much, but we have some.
I don't need much. I can get by. A little help from my friends.
Yes.
I gotta say though, for the next stream, like it was really nice having that the like down tempo, lo-fi, chill, whatever beats to study and relax to going on in the background. And it would be nice to sort of like have a setup like this, but be able to like play music through speakers or something like that, but also have it on stream. I don't know. There's so much complexity that you can get involved in your stream. And
Lo-fi chill beats like a System of a Down self-titled.
oh yeah, just like that. Very lo-fi, very chill, very system, very down. So let's go over here. This is our little micro, little scribby-doo. Get y'all cleaned up. But actually, what's awesome about this? All right, I'm gonna do some. We call this. If you like go get a board assembled, they have something called AOI, which is automatic optical inspection, which is sort of like using computer vision to make sure that everything is all set in the right place and all that kind of stuff. But come on. What I am trying to do is some manual optical inspection. If this frickin' thing will focus, man. Well, heck. Oh, there we go. And it's gone. So I'm trying to try as I may, and doing it poorly at that. There we go. Is zoom in right at those leads and see if I can make out if there's any short circuits. Whoop. Yeah. Oh yeah, look at that. Cool. So you can see, honestly, that is probably like a little bit too much solder paste, because you can see it kind of like bubbled up there. Not a huge issue though, I don't think.
You could clean it up slightly. You could use a desoldering braid to show how you would clean that up.
Yeah, I guess I could.
I guess you could.
Yeah, that'd be cool, actually.
Some rosin flux.
Nice. Thanks, Ted. All right. So, what I'm gonna do then is show you how to remove this. So it's like, yeah, dig a hole, fill it back up, dig a hole and fill it back up. You just cleaned it, now add some more flux. So what I'm gonna do is put a little bit of this little flux gunk here, and here, different corners. And then what I'm gonna do is take this stuff, which is like, it's a copper braid. So it's got a lot of surface area, and what its sort of principle of operation is like, you heat it up, and the solder has a higher affinity for that desoldering braid than it does for, you know, whatever the thing that it's stuck to. And you can remove little bits of solder. So basically you like heat up everything at the same time, right, with your soldering tip, and then alright, you can see just kind of touching it up there. It removes the bulk of it. There's a yeah. If you do what you're supposed to, you shouldn't have to do this, but we're playing fast and loose here. If I can zoom in even further, because we have some what do you call them? non-camera microscopes that get you pretty darn good zoom in. I might need to switch to one of those for a sec. So I'm just trying to make sure that we have proper connection without too much solder. Yeah, boom, there you go, cool. And then this side, you can see there's a little bit too much. Might be able to just use the soldering iron as our desoldering wick. You left a little blob there. Yeah, that's gonna need to get that with a little bit of desoldering wick or some alcoholic goof off. Dang, I'm sorry everybody with all this focusing brouhaha.
Sorry, you have to go. Don't leave them all behind. Face the truth.
Face the truth. Mama! Ooh, ooh, ooh.
Whoa, 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 whoa.
Yeah. Which, my mom was supposed to be on this stream. She's supposed to watch me make circuit boards. Alright, und then the last side. That all feels pretty good. Just sort of tapping it lightly with the soldering iron. Alright, that's fine. Back again with the desoldering, or the goof off. Oh man. Yeah, so the cleaning is sort of it's an intermediate step. You know, even if you're gonna do more soldering and stuff, it makes like adding more solder and doing other stuff easier later. And it also, because like the flux can discolor and like, you know, cause some gross sort of, I don't know, artifacts, I guess you'd call them, or it makes it easier to debug if you have a clean board. That's basically what I'm getting at here. Voila. Oh, it is so pretty. Oh, and in cleaning, I created a little short there.
What does that board do again?
This board currently does absolutely nothing. No, it's this board is it's a breakout for this microcontroller, and it also connects the microcontroller to a 7-segment display. So as you can see, I'm running the soldering braid over the top of all of these pins here, and that just sucks away all the solder. I might want a different tip for this. Maybe the same one. Who knows? Now, I'm gonna do this fun and exciting exercise because I can't find the right parts. Is I've got all of these little, like, it's meant for wire wrap, which is like, I don't know, doesn't seem to be as popular these days, but there's a way of sort of like, rather than soldering wires together, you have a tool that you wrap wires around the leads and connect them together. But it's very thin wire, solid core, 30 gauge. And what I'm going to be doing is instead just using these as little like pad extensions so that I can attach, you know, this little end here to this pad, and then the long end that comes off of it Come on now. This long end that is unclipped, that's going to be attached to a through-hole component. So just a way of doing some reworking. So again, the more flux you have, the better. Oops. It's like I melted the tip a little bit with that hot air gun. But no matter, we shall still get it to work. Perfect. So this is a, how many pins here? 14. 14? Man, it's a lot of pins. Honestly, I would much rather just test that this thing was working before I went and did all of these guys. Alright, so change of plans. Rather than get the shift register all hooked up, only the parts coming from the processor itself. So that's going to be the shift reset, shift DSA, DSB, and so forth. Those guys, I think what I want to do is just attach wires to those particular pads on the footprint over here, and that way when I power this board up, I can write some quick demo code that will like toggle those pins specifically. So I can treat them as GPIOs, and we can demonstrate basic functionality before we try to hack something crazy together. So I think that's probably going to be a good first step. So what is it? It's going to be shift clock, shift reset, and then shift DSA and DSB. So 4 GPIOs. That's enough to work with for a little bit. So this is going to be a kind of manual process instead of the hot air gun thing. So let's see. So it's going to be these bottom two guys here. And then what I'm doing is taking some solder. I am tinning the tip. I'm going to tin this pad, tin all these pads. And then, as needed, we'll remove the solder paste from them. So I know I got shorts in there, but shorts are not the end of the world. They're easily corrected. All right, so there's the first one. Let's see if we can touch that up a little bit. Voila. Very cool. And then again, 3 or 4 more times. Did you discover something, Ted?
Yes, I did discover something. I remembered something.
Ted remembered something!
I was thinking I want Chipotle for dinner, and they opened one by the Whole Foods. That same plaza.
Oh, nice.
Yeah, it's right. There's a Chipotle right around the corner.
Hells yeah.
When trying to do that when they close.
Oh, they closed at 10, but I mean I could eat at any time. Would you like us to bring you back with them, Patrick Lloyd?
Yeah, sure. Wow, way to dox me on stream.
Patrick Smith.
Ah, yes. No, yeah. Can you bring me back a case of some Swedish fish? A quesadilla. And I will take a break from this stream probably and do a intermission, so I can let you know what I'm all about.
See you guys.
See you, Zach. Okay, so these guys are both in place.
What are you doing for Thanksgiving?
I don't know. I need to go back and see my family eventually. One of these years.
Look at this year's the year.
I don't know. I took last year as the year, but I did it go. I don't know. What was I gonna say? Last Thanksgiving I spent it with Dan. I don't think Dan has any intentions of going back home. May have to spend Thanksgiving down in Santa Cruz. Yeah.
Okay, so just removing the solder bridges there. So those two
Solder
guys.
bridge.
What's up?
Happy little solder bridge.
Happiest little solder bridge. Happier than you could ever imagine. So then these guys, the DSA and DSB, those are the only other two wires I need to attach. Those guys are going to go, those are in the upper left 2 pins. So. And this happened off screen, but I have a multimeter here and was checking continuity to make sure that those two things that I just soldered, make sure that they're not accidentally touching each other on the pads, because that would cause problems, potentially. It's like, I don't know, I've heard mostly from like video games and stuff, but it's like when you're firing a like some sort of like long range rifle or something like that, you're supposed to like take a breath and sort of like stop breathing and like tense everything up before you take your shot. And like it feels the same way for like certain soldering things where it's like, all right, super teeny tiny pad that you're soldering to. It's like, take a deep breath, hold it, and attach the iron to the to the tip.
Stay on target.
Stay on target. Remember your training. Alright, and if I can just get that little guy attached, we shall be golden. Whoop. Whoa. Accidentally touching the wrong things here. Oops. It's causing all sorts of problems. This might be good enough. At least for our purposes anyway. So you can see it's tacked down at that spot. Not super great. I don't know. So, something that I definitely struggle with is, that lovely cliche, perfect is the enemy of good. But even in this case, like, even good is the enemy of getting something done. So I am just trying to get it as basic as it needs to be without too many bells and whistles. Just as a sort of like, this is a proof of concept. This doesn't need to be anything special, man. So it looks like, from what I can tell, You see that's pretty secure. That other wire is also secure. These guys, secure. All right, and I want to make sure that these things are not accidentally going to, like, you know, you maneuver them around. I really should just fix this board to the surface here. Kind of like wiggling stuff, but something funny, Ted, huh?
Yeah.
So now what I'm gonna do, I'm gonna heat up the hot glue gun, and then put a big old blob of hot glue right there over those leads so that they don't move, and it provides some strain relief. So that way, if I tug on the wire, rather than like all of that force transferring to the mechanical connections on those pads, it instead just pulls on the mechanical connections between the wire insulation and the hot glue itself. So, and what's really, really nice about hot glue, and I find this comes in so handy, especially for electronics, is that like when you're doing, when you have hot glue and you like splort it all over something, and it's like, oh no, it's never coming up. But the thing is, like, if you have isopropyl alcohol, and it needs to be alcohol, it can't be a stronger solvent like goof off, but isopropyl alcohol, if you kind of like put it around the edges, it gets underneath hot glue really easily, and it makes like essentially any sort of hot glue bond completely removable. So it's nice for making, like, you know, I don't know, it makes it feel a lot less risky to put hot glue all over something, you know, because it creates a nice semi-permanent bond, but it can be removed really easily with alcohol. So let me go warm that up real quick. All right. What to do in the meantime? I'm gonna take. You know what? I think this might be a good stopping point for now, just to sort of, I don't know, take a break, maybe get some dinner, do something like that, and then maybe come back and do the rest of this stuff. So, all right, well, all y'all, thank you for watching. Tune in next time, and yeah, we'll get this thing to Blinky eventually. So hopefully tonight. See you then.